not that r and theta are difficult. It's just that we have not get that much experience dealing with these kind of equations. But there's a uniform way to graph any function. Plot points. You can always plot points. You can always try to find theta values, and then according to this equation, you find r value, and then you plot the points right here. You can always plot the points. By trying to find more and more points, you will be able to find the sketch of the curve. Right? That's the uniform way. You can deal with xy equations, RC equation, any kind of equation. But usually, I don't want to do that because I want to have a nicer picture, and also I want to have equation relations. All right. So here, I can easily find some special cases, even though I'm not plotting points, but I'm going to plug in some points and see what they are to give me a general feeling. When theta is equal to 0, cosine theta is equal to 1. So this is going to be 1 over 1, r is equal to 1. So on positive direction of axis, I can have the point to change from 0 up to 1, okay, right? I can choose theta to be equal to, for instance, pi divided by 3. If theta is equal to pi divided by 3, then cosine theta is equal to 1/2, right? So it is equal to 1/2, so r as the radius will change from 0 to 2. So we'll change from 0 to 2. So essentially, for every angle right here, I'm supposed to find the smallest radius, which is just the 0, and the largest radius, which is given by this function. And then all the points will be between these two radii. Are you with me? So if I move the angle, I'm supposed to have the largest radii coming from the function here, and then the points will be bounded between these 2 points from the origin, from the longest distance. All right? But I want to look at this equation more closely, and I want to see what exactly is this guy. If r is equal to 1 divided by cosine theta, where theta is the angle right here, okay? I can indeed rewrite this equation by cosine theta is equal to 1 divided by r. Am I right? Which is just a simple translation between this fraction to that fraction. So cosine theta equals 1 divided by r. When I'm dealing with trigonometries, having a right triangle always helps. Am I right? So if you're dealing with cosine, sine, whatever tangent function, if you have a right angle, it's going to be extremely helpful. So cosine theta in a right triangle is defined as the portion of this piece with the hypotenuse, right? What's the English word I'm looking for? Hypotenuse. Adjacent over hypotenuse, right? So if I have a right triangle coming from a point down to 1, I have a right triangle, and in this right triangle, cosine theta is exactly equal to 1 over r right here. So this is indeed the r I'm looking for. Are you with me? So in order to find the longest distance r, or in order to find the dependent variable r according to theta, the only thing I need to do is to have a ray going from a theta angle. And then I have a right triangle going up from 1 right here. And then this longest side in this right triangle will be exactly my r. Right? Because in this right triangle, cosine theta is equal to 1 divided by r. Therefore, r is exactly equal to cosine divided by cosine, 1 divided by cosine theta. So instead of plotting a lot of points, I just draw a vertical line, which is going to be giving me a right triangle. And this right triangle is formed by the angle theta and this distance 1. Okay? And within this right triangle, this side is exactly what I'm looking for. Okay? Are you with me? Are you with me? So if you haven't completely convinced, you can go back and see, you draw your own right triangle and see how you can get these trigonometric relations. So in this right triangle, I always have this r as the hypotenuse, which is coming from this function, which means if my theta is changing from 0 to pi divided by 3, this whole thing will be the region right here. Right? This whole thing will be the region right here, because for any ray coming from a r theta angle, so this distance is going to be the restriction for the radii. Right? So from 0 the longest distance. So this is exactly what I will have. So this is indeed our simple region, but after I put it into XY plane, this is an extremely simple region in XY coordinate system. You know what I mean? So polar region will deal pretty nicely about a disk, pieces of a disk, but XY type of region will deal very nicely about triangles. Right? Because so for triangles, you always have these straight lines. Straight lines have a very simple equations in X and Y. Am I right? So if I want to re-evaluate this double integral by using X or Y simple region, for instance, you can try to use a Y simple region. So X is bounded by two numbers. Y is bounded by a lower function, Y equals 0, and upper function, Y equals the slope of
2
multiplied by X. So what is the slope for this guy? The slope is actually Y over X. This is 1. I already found this distance is 2. This is actually square root of 3 divided by 2. All right? This is actually square root of 3 divided by 2. So the slope is not exactly 2. The slope is Y over X. So the slope is actually square root of 3 divided by 2. So I have the upper function right here. I have a lower function Y equals 0. So I can indeed rewrite this equation into a Y simple region, which is going to be equal to from 0 to 1, from 0 to square root of 3 divided by 2x. And then here is the tricky part. I need to translate r theta back into x and y. But when I'm writing it in a polar rectangle, so Michael.
Sorry, can you repeat? How did you find the slope again? The right 3 or 2?
Okay, so I want to find the slope for
This one.
this rig, all right? The easiest one you can see is in this right triangle, I have 1, 2, so this side has length square root of 3 divided by 2.
Oh.
And the slope is the portion of y over x. In other words, if you have this angle, which is given by pi divided by 3, okay, you can also find this from the angle here. So if you have a straight line passing through the origin, forming an angle of 60 degrees, you can also derive what a slope is. All right? You can also derive the slope coming from this angle directly without even looking at this right triangle. Okay? Questions? So I will be able to transform the region from a R simple region to a Y simple region, dy dx. But here is another important thing you have to pay attention to. When I have this double integral in polar rectangle, the integrating function is indeed different from R to Q. Are you with me? The integrating function here is actually R squared. Because when you write down the double integral in this polar form, it's actually the integrating function f multiplied by the extra factor R. So we're not exactly integrating the function R cubed. We're actually integrating the function R squared. And with me? So we're actually integrating the function R squared. So when I'm transforming this in R simple to xy, I'm supposed to have R squared, which is x squared plus y squared dy dx. Okay? As long as I can accomplish that, the following work will be pretty simple, because now you're only dealing with polynomials. Okay? Now you're only dealing with polynomials. Now this is probably the most challenging question you will see in double integral. This one is challenging in both cases. You have to transform the region from one type to the other. All right? You have to transform the region from R simple region to a rectangular region involving x and y, x, y coordinate system. You have to also be careful about transforming the integrating function. Right? So from xy to r and theta is pretty simple. From r theta to xy, you have to remember getting rid of a factor r. So when you go from xy to r theta, you're adding a factor r. Going back, you have to get rid of this r factor here. Okay? So this is a pretty nice evaluation. Okay? And you can evaluate the following by trying to find the antiderivative for polynomial functions. Questions? And you can do the following. Okay? Questions? So There's one application about this double integral, which is so-called average quantity. So I want to mention it in the very end. So this is the problem. I want to find the average distance of the points in 0 divided by is less than r is less than 4 with the origin. Okay. So the average distance of the points in 0 is less than equal to r less than equal to 4 with the origin. First of all, if I look at this region, now we should be pretty smooth about what this region is. This is disk, center at 0 with radius 4. Okay. So this is nothing but a disk, center at 0 with radius 4. So I want to find the average distance. I know picking any point in this disk, I'll be able to find the distance between this point and the origin. All right. So if I have a point r and theta in polar coordinate system, I can easily find the distance between this point and the origin. That's given by r. Am I right? That's just r. So what is the advantage for us to use polar coordinate system? This is one of them, right? So if you have the point written down in polar coordinate system, r and theta, you know immediately this r is the distance, right? Whereas if you use x and y, you have to x squared plus y squared and then take the square root. Here the distance is where you can gain an advantage for using polar coordinate system. So picking any point, I can easily find the radius r is exactly the distance between this point and the origin. So I want to find the average distance, which means I need to find the integral of all the distances over the area of this region. Okay, so area of this region R, and also multiply by the double integral of the distance function R, and then dA. So this is the formula for the average. Okay? So it is the average for the simple reason. The simple reason is I'm taking the average, which means the average of this function, the distance function, right? So this is essentially a function. In order to compute this average of a function, I need to take the double integral of this function. Okay, so this is actually the function. So let's make it more general. So if I want to find the average value of a function, I need to take the integral of the function over the region and then divide by the area of this region. Right? Would you agree with me? This is indeed the definition of the average of a function. Right? Any quantity. If you have a quantity, for instance, I want to find the average score of the first midterm of all of you. What you need to do is you need to add all the scores together and divide by the number of. Yeah. Right? So that's the average. Here, I don't have a discrete number here. Okay? So the summation will be replaced by an integral. And the number of u will be replaced by the area. Right? So number of u will be replaced by the area. So this is indeed the average of whatever quantity you have. Now I'm computing the average of a distance. Therefore, I'm taking the integral of a function r. Okay? A function r. So for this particular function, the function is the distance. So I need to integrate against r dA. And then the area of this region, which is a disk. Not only we knew the geometric formula, but actually we use double integral to verify that formula. The area of this disk is pi to multiply by the radius squared, which is 16 pi. All right? 16 pi. So I also need to evaluate this double integral. This double integral, naturally, I want to use a polar system, right? I want to use polar system because this integrating region is a disk. If your integrating region is a disk, no brainer, you have to go to polar. Okay? You gain a lot of advantage here. So it's from 0 to 2 pi, from 0 to 4. R is my integrating function, but also I have one additional factor coming, r dr dθ, and then divide by 16 pi. You can do the following. So this one is the integrating function for of polynomials, and then divide by 16, you'll be able to find the average distance. Now I want you to guess what the average is.
1.
Right?
0.
So the average will vary from 0 to 4. Right? So at least I know this average is definitely between 0 and 4. It's not going to be smaller than 0. It's not going to be larger than 4. So when you have a shorter distance, for instance, if a short distance is 1, you have a less point having distance 1. Right? So the longer distance you have, more points you will have. So this number will tilt towards 4 than 0. And it is definitely not the middle ground of 2. Right? It's not going to be the middle of 0 and 4. So you can try to compute what the average is and convince yourself why this is indeed the average of the distance. Okay? So it's a pretty interesting application. Questions? So next, we have to go to triple integral. So I want to give you a little summary here. So we have done not too much. We're still looking at R, F, X, Y, dA. So this is all the things we have done. Okay, so we are taking a double integral of integrating function F over a integrating region R. Depending on what function you're getting, and more importantly, depending on what region you're getting, we have different types of the region we can identify. Okay, so the key information about all the integral, double integral or triple integral, is to identify the region. Okay, so we begin from the rectangular region. So R is equal to A is less than equal to X is less than equal to B. Y is bounded between C and D. Okay. So if you can do that, then you can rewrite this double integral into from A to B, from C to D, F X Y, dx dy, which is also equal to from A to B, from C to D, F X Y, dy dx. So it seems like a long time ago, but we did begin from a rectangle. It's just that this type of region is too simple to even discuss anything. For the reason that you can switch the order